Can you hear me all right?
Yes.
Is that better? Okay. I have a quiet voice, even though it's a small room. I want to be a little careful. So I'm going to talk about a random collection of things. This is kind of a bizarre style of talk for me, but I hope it's useful. I want to cover a lot of ideas and topics, and this is largely related to some recent thoughts I've had as I've been having increased collaborative research activities with people in precision medicine and other areas. And so this is a picture here of the day in the life of a patient with type 1 diabetes. We'll talk a little bit more about what's going on, but these include insulin boluses, blood glucose level, food intake, exercise activity. The size of the circle is the magnitude, and the center of the circle is the time point. I'll come back to that and what we're thinking about with that. So I'm going to talk a little bit about precision medicine, but I want to try to talk about it from a conceptual point of view and about how we can frame the question formally. And I think a lot of us are doing this anyway, so this won't necessarily be new for this group. But I think it may be one of the things I say, or the way I say it, may be useful as you work with collaborators in explaining concepts related to machine learning, precision medicine. I'll talk a little bit about machine learning, some advances on the interface. I want to talk a little bit about artificial intelligence also. Just a reminder, this is the big area that machine learning is a part of. So it's bigger and broader. And I think there's some interesting, important things we should be aware of and think about there. And then I think I'll have a few minutes to talk about type 1 diabetes, mobile health application of precision medicine that we're working on. I'll talk a little bit about some future direction issues and some concluding thoughts. All right, so this is the book that Erica Moody and I edited that includes a lot of state-of-the-art discussion of precision medicine, published in 2016. It's probably out of date at this point, but it's still, in terms of a published volume, it's a good introduction to the area. What do I view? I think precision medicine has many, many names, but I would like to talk about the definitions that I think are useful that separate precision medicine from biomedical research as usual. So basically, I view it as data-driven decision support for treating patients in the presence of heterogeneity. And one of the primary ways that we do this is through the estimation and evaluation of dynamic treatment regimes, dynamic treatment rules, and various variants of that. In other words, specific decision support. And the treatment that these prescribe include drug choice, administrative actions, dosing, timing, potentially modifiable risk factors. In other words, we might look at things like the consequences of smoking cessation, and or other potentially beneficial actions for patients. And also, as we are concerned about statistical aspects and properties, what we develop needs to be reproducible and generalizable, empirically and inferentially. Precision public health is just the application of these principles to larger entities for which we might give treatments, include families, or treatments or actions, families, communities, clinics, social networks, schools, and other entities, regions, geographic regions. There are other possibilities. Potential treatments could also be policies here. One might look at this policy at the county level, the state or national level, as possible actions that one might take. And precision health is a union of all of these ideas. And one of the things that is important about this particular approach that is contrary to industry views precision medicine, or at least some sectors of industry, that is, much of the time they're focusing on narrow subgroups and how to treat that subgroup. Sometimes it's because that subgroup has a well-defined mechanism they can target with a drug. And we're focusing on how we would benefit a population. There's been an interesting series of articles in the Journal of American Medical Association which look at precision medicine. One of the critiques is it tends to focus on small subgroups at the expense of the population. So what we're doing is we're using a population-based approach to precision medicine. In other words, if we come up with a method, we're interested in evaluating it in the population. If the dynamic treatment regime is estimated, will it work in the population? How well will it work? if we come up with an automated control method of adjusting for factors to control type 1 blood glucose level, for example, will that adapt to for a variety of individuals in a population? Will it be effective at adapting to their mechanistic specific characteristics? So that's something else we care about. So those gradients are important. And here's a little bit of some simple ideas. The kinds of things we might have that go into this, globally speaking, we would have tailoring variables. These are the variables we believe are important in how the treatment may vary, and how the subgroups within which treatments homogeneous may be defined. Choice of treatments and potentially modifiable risk factors are A. A could be a discrete set, it could also be a continuum, or it could be something more complex. For example, it could be a particular topic for textual interventions. Vector of outcomes or utilities, Y. This is a thing that we're maximizing in various constraints or other various ways of looking at the variety of outcomes. And so often we think of having a single thing we maximize, but in medicine that's not always the right thing to do. So we really have a triple of data, but we could have that triple replicated over time, even on a continuum, or expanded. In the case of certain kinds of dynamic regimes, the variables we're using for Taylor may actually increase in dimension as we accumulate more history, and that's fine. The dynamic treatment regime is the algorithm that we're seeking to estimate that makes a single recommendation for treatment. For the single decision case, we make a single recommendation based on treatment. For multiple decision, make a series of interdependent recommendations. And then continual monitoring is another possibility. As I'll talk about an example in mHealth where we need to continually monitor and perhaps give interventions along the way. And one can have more complex structure, for example, intervention on a network in time, intervention on a network where only part of it is known, various other things. So this is useful in controlling various infectious disease outbreaks and other types of situations. One of the things I think is really important as we work with collaborators is for this kind of research, heterogeneity is valuable. It's not just not a nuisance, it's actually essential. As I meet with collaborators, and we look about observational or randomized data either, we really want to study the heterogeneity, make sure it's representative of the goals, the long-term goals of the population we want to target. And so this is different than clinical trials where homogeneity is better and easier. We really want heterogeneity. And I want to mention too that the heterogeneity is not just in the X variables or the kind of individuals in our study, it's also in the treatments and how they distribute across the X's. That really matters as well. And all of you know this, I'm just trying to give some way of organizing these thoughts I hope is useful as you think about collaborating with investigators. So the dynamic treatment regime is a function of X that gives us an algorithm for how to treat A, to maximize Y, or if it's a multivariate Y, to achieve some optimal outcome in terms of Y based on how we're deciding to balance and constrain the different outcomes. A very standard approach is to use regression modeling of some kind. This is what we call a Q function for the single case. Even in the case of reinforcement learning, where we have a series of models we have to fit, regression model under constraints or after maximization and various other ways is still a very powerful tool. And this is a good way to think about solving this problem. But these have to be causally valid in the sense that we have to be able to, they have to work as we vary over A and over X. And so it's not just prediction we're interested in. However, oftentimes we're really interested in the direct estimate of the policy. And in that we sometimes may want to not have to regress the whole model or estimate the whole model, but maybe parts of it, or think about the estimation in a different way. And before I talk about this, I just want to mention that some of my collaborators have, with the advent of Gaussian processes and deep learning, it seems like modeling is really, really there's less assumptions we have to make. And so what's wrong with modeling? Well, sometimes I think it's good. You have a lot of degrees of freedom to worry about, and with deep learning or Gaussian processing, you need a pretty good sample size. If you're very careful, you can do a couple hundred, but you got to be kind of lucky for that to work out. To really pull out the benefits, you need thousands of patients. Whereas policy approaches can sometimes begin to work very well with sample sizes in the small hundreds or smaller with relatively high dimension. So thinking about the policy approach to estimation where we target the policy versus regression or things in between is something that can help us achieve better performance depending on the context. And in biomedical research, we will always have small populations that are important. That's very important to remember. And we still want to be able to use all of these powerful tools. And so here's another way to see how to isolate the, and I'm presenting this formula not because I don't think you guys know it, but because I find it's very useful and interpretable with collaborators. So suppose our outcome Y is some function, prognostic, has a prognostic component, function of X, then it has an interaction component with the treatment, G, and residual error. Turns out that you can, if you allow the residual errors to have variance depending on X, it turns out that this is a tautology. Wherever you have XA and output Y, this has to be the case. It just involves taking a sequence of conditional expectations. So this isn't just a convenient model, it's actually a tautology of sorts. But in any case, what we care about here is really the sign of G, whether it's greater than 0 or not. That's really going to determine whether the treatment for that person is going to be beneficial or not. And this allows us to not spend as much energy on estimating F instead of G, but it allows us to also break down what's going down and separate out prognostic versus what I'm calling prescriptive components. So the G is prescriptive, the F is prognostic. Those two things are important to remember because many people conflate these as they do precision medicine work. They really focus on the prognostic piece, and that's useful if you're doing prediction, but it tells you absolutely nothing about what treatment to give them. Whereas if you're focused on that, then the prescriptive piece is important. And again, you all know about the propensity score, but I think educating collaborators about propensity score is very important because this helps us understand the nature of the homogeneity of treatment across X. I want to say that we do allow for the choice of treatments to vary by X, but you should be in control of that. It shouldn't be just solely dictated by how your data is sampled. And the causal methods are the foundation of this approach, are the way of thinking here. We care about the potential outcomes. However, we tend to care also about the potential outcomes behavior conditional on X. That's very important for precision medicine, whereas that's less important for standard causal methods unless you're worried about transporting, and then it's only there to make sure that your treatment maintains its benefit or you know the size of the benefit. But we care a great deal about the treatment as a function of X because that is how we do the precision medicine. Okay, so that's just some ideas. Many of you know a great deal about machine learning. And I just want to remind you the sort of things that machine learning involve. Unsupervised learning, as was discussed in the previous talk. Supervised learning is regression, data-driven decision-making, classification. Partly supervised, and there's many other more semi-supervised, and there's many sort of possible tasks. What is the statistical contribution about this? Well, in statistics, we often care about inferential aspects. And inferential includes consistency. Is it estimating something? I call that zero-order consistency. We like to know that first before we really believe a method. We want to have some verification. And I want to say that if I were giving this talk 5 years ago, I would probably have to be very careful how I said this to a CS or a stat audience, depending. However, statisticians are becoming more savvy with computational methods, and computer science researchers are becoming much more savvy with statistics. there is a healthy interface of these fields. And so I don't feel that's necessary, but it's a reminder that statistical thinking is very, very important here. Another thing about precision medicine is much of the techniques that we discussed and concerned about are discovery-based. And we want to identify this dynamic treatment regime or something about it that we can use, and then we would often go on to a validation stage later where we may be able to use standard clinical trial methods. But it's very important to understand this difference, because the first time that I've interacted with some of my collaborators, they're going with the NIH hypothesis-driven model approach, and they realize, what's your hypothesis? Well, we don't know our hypothesis until we've estimated the dynamic treatment regime. So working with NIH grants so that you can articulate this as a distinct approach versus hypothesis testing, and when necessary, you know how to couch it as a hypothesis, even though it's discovery-based. But keeping and remembering the importance of the distinction between discovery versus validation. Okay, a couple other things about machine learning. There's a couple tasks that really are very distinct from the regression classification type things we think of. Reinforcement learning, both on policy and off policy, is one of those important distinctions. This is really something very different. You can use embedded models such as regression models to get it done, as you would in Q-learning, for example. You can even use embedded deep learning and Gaussian process and other techniques. One of the big differences I find as I collaborate with machine learners who are outside of who are maybe not as involved in biostatistical related research is the distinction between on policy and off policy. Much of the fantastic developments, including the AlphaGo AI becoming world champion, are based on on policy reinforcement learning, where you can simulate the different policies you have and see the consequences of them in your procedure. Off policy is what we have in much of biomedical research, where we have an observational study or randomized study. We only get to observe each person's experience on one sequence of treatments. We can't keep trying with the same people different sets of treatments. And so that's a very important difference. And there's a lot of mistrust among machine learners that are new to this of off-policy techniques, generally speaking. And that's why some of the theoretical proofs we have on consistency are very, very important. But it's also important to keep asking these questions, because even with our theoretical proofs, there are conditions, and sometimes there are situations where our off-policy approaches may not be as secure as we think they are. So it's important to think about that. I already mentioned the role of causal inference. It's a framework that we embrace in this area and use. And these techniques are very useful for precision medicine. Okay, so just a little bit on some of the DTR estimation settings. Single decision setting, regression, maximization is valuable. They're both frequentist and Bayesian tools, can be used for this. Especially with Gaussian processes, this is a very powerful, and Bayesian neural nets. These tools are very, very useful. Machine learning generally is very, very helpful. And I will say there is occasionally confusion as one works in machine learning, because Bayesian frequentist paradigm is not so dichotomized, and people go back and forth and do approximate Bayes, approximate frequentist, and everything in between. And it's easier just to not worry about it too much and just do what works and try to learn from everybody. Also, theoretical frameworks that are emerging are very comfortable to contain both of those approaches, both Bayesian and frequentist paradigms. 5 years ago, I would have had a fight with one of you out in the hallway with that comment, but I think now we're pretty much, we recognize this, and we're moving forward productively. In the multi-decision setting, you absolutely need reinforcement learning of various kinds, and Q-learning is very, very useful. It's sort of like, for off-policy, it's often a go-to method because it just works so well, and it's easy to diagnose to a certain extent. There's software for it. Probably at this conference, many of you are aware of, if you haven't, the outcome-weighted learning. This is the idea of focusing on policy I mentioned earlier. And this actually has a long history in many disciplines, in marketing, in economics, and other areas, in engineering. But some of the things we do in biomedicine is enough different that we have to reconstruct theory for it. And sometimes it's a little confusing to people who begin to talk across these different disciplines, because what we care about in biomedicine is sometimes different to what they care about in engineering applications or marketing applications. For example, we're not quite as comfortable with taking as many risks with patients as the marketing people are with marketing strategies. People don't die most of the time because of marketing. That's not to criticize, I'm just saying that that's different, the focus can be on different things. And so I talked about some of the benefits of this already. And a number of extensions of these ideas. Time to event outcomes with censoring, that's something that's uniquely biomedical. That raises some interesting challenges in machine learning. Continuous treatments, interpretable dynamic treatment regimes, i.e. list-based. Multi-decision setting, the finite horizon case, which would be the case where you have a finite set of decisions, such as in chemotherapy treatment. Infinite horizon, continual treatment, as you would have with mobile health interventions, including type 1 diabetes. And I have this little infinity sign here because what we mean by infinite horizon here is that we're applying the same rules over the same algorithm in time, but it tends to lead to treatments that adapt over time. But you think about it in the infinite horizon because it's really more indefinite. You don't really want to change the algorithm itself. You want it to be able to adapt on its own to the changing time. However, one of the things that we're thinking about working on is that we really believe what's really going on with, say, type 1 diabetes is that locally there's enough mechanistic stability that you can do precision medicine, and then as people's dynamics changes over time, maybe they are really getting better at exercising or the opposite, and their dynamics are changing, your method should be able to continue to adapt to them gradually if you use careful, not too greedy approaches for exploration. All right, I've said a lot of things that I may not have defined, but I'll try to make this concrete if we have the opportunity later. Managing multiple competing outcomes is very, very important in biomedicine. We have a lot of situations where efficacy is important, but we also care about side effect burden. And inverse reinforcement learning, it turns out to be surprisingly useful. I won't have time in this talk, but there's some situations where instead of just using observational data because we don't have a randomized trial, sometimes we can learn about what physicians are doing. Reinforcement learning normally looks at, just see can we mimic what the physicians are doing. But there's ways that you can actually go deeper by modeling and looking at what the physician does, that you can actually figure out what the physician is trying to do, but they're doing it with error, and then figuring out how they can do it with less error. And so this lets us use observation data to go beyond just mimicking, but to actually learn and improve treatment. So some recent developments in machine learning, there's this very interesting counterfactual Gaussian process work by Shulam and Soraya at Hopkins that I think has some potential. This goes a little one step beyond regression modeling to allow you to be able to do sort of what if analysis. What if I tweak the treatment a little bit here and there? It doesn't go all the way to do full decision support where you really want to know what's optimal, but it can allow you to try a few things out and maybe, so it's decision support certainly closer to dynamic treatment regime than prediction-based methods, but it's not quite there, but I think it's an interesting step. There's outcome-weighted deep learning, which is an interesting paper in Statistics in Medicine that does a very clever job of using deep learning to find treatment regimes using outcome-based learning. And there's a paper that is sort of raising controversy right now on off-policy deep reinforcement learning. And one of the challenges with reinforcement learning in complex settings is that it's really hard to do inference for it. And so so sometimes you have to go take turns trying to figure out the policy and then modeling the process as a Markov process and thinking about this. So kind of doing simulations based on the observed data. Now, again, this is not a published paper yet, but it's an interesting idea in that direction. Okay, so now something completely different. For the last 3 years or so, I've started broadening my work from machine learning to more general AI. And just want to mention briefly that artificial intelligence is this big area that involves trying to figure out how to do things that essentially try to improve on what humans can do, but it's just generally how do we get computers to solve various problems that involve making decisions and other kinds of different kinds of navigation. And machine learning is a very important piece of it, but it involves other things as well. So I'm going to talk a little bit about this, and probably a lot of you know the history of AI and so on, so I apologize for repeating. I'm going to just highlight on some things. So in the early 1950s, when AI really started, although there was science fiction writing, which is before that, but when it really people started thinking about this, one of the earliest conceptual developments was the Turing test. The idea of I talk to this machine and it acts so much like a person, maybe it is artificial intelligence because I can't tell. But the problem is that human beings make spelling errors and we take a while to solve math problems. So that means the computer would actually have to be dumbed down a bit sometimes to sound like a person, right? And so this raises the issue of what do we really want these AIs to do? Probably not be exactly like people. Maybe do the things that people are really good at better than we do, but not necessarily be exactly like people. And what kind of tasks can they perform? Can they reason logically? This was one of the earliest areas of artificial intelligence. Can they be able to make optimal decisions? Now that question is to this day very important because that's really one of the holy grails of AI is to be able to get computers to make decisions with the available data they have. And this is really what precision medicine is doing very specifically, is trying to provide decision support. So there's a very important link there. How about to act optimally generally? So this is AI-driven robotics for where you're trying to have control, walk and not fall over, for example, and other things. Now, how about some more challenging things? What about reason morally? What will it take for us to get computers to reason morally? You read the AI, the science fiction, that's probably going to be like it's never, right? I just don't think computers could do this by themselves. What about creating something surprising? So I had an interesting conversation with a colleague of mine who is actually in anthropology. That's his area. And we were talking about what AI can do, and we were thinking about, I'm a musician, I like to write music, classical style. And I was thinking about some of the tools that have been developed to sort of mimic paintings and art, some of the generative AI that creates paintings and creates Mozart-like music. The challenge is that those pieces are locally similar to the music of Mozart, but really we don't need to write more Mozart music, especially stuff that already sounds like what he's done. It's great music, but what's really powerful about the great art is it gives us something surprising that we haven't seen before. If you look at Mozart's late work, there's stuff he did that's outrageously different in great ways than his early work. Similar with Beethoven. Beethoven had a lot of surprises with his music. So how do you create something surprising? He talked about his view, his colleague of mine, he's a sketcher, does drawing. When he looks for a subject, he looks for something that's a little surprising, but not too shocking so he can look at it like a dead body or something. He looks at things that are appealing to draw, but are still interesting. And so can we have a computer learn how to create a piece of art or music that's surprising and good at the same time? That's really tricky. And so those are some things to think about. I don't have answers, I'm just saying that these are the next steps that are well beyond what we can do right now. So what do we want computers to do, practically speaking? We want them to help make rational decisions to achieve predefined goals. So, decision support. Goals are usually related to optimizing a predefined utility. So again, we identify something we want to optimize and we seek to do that, or, as I mentioned, a vector, a constellation of things we want to optimize. Can a computer decide what utility it should use? Right? That's a little tricky, because that's once we get that utility worked out, we can get a non-parametric model, we got a decision, we can work out a decision using our existing techniques, but that involves a lot of human help, right? And what can we learn about AI by studying the human brain? It's really hard to reverse engineer a human brain. It hasn't been done before. But there are some things we do really well. The things we do poorly too. Sometimes we make terrible decisions, right? But memory and inference are key to good decision making. So memory, we have the information in our head. Inference is how we process it and think about what to do next, about the logical steps, or even beyond logic, creative steps. So let's talk briefly about a brief history. Again, I'm not going to go through this whole slide. Really, the important part of the slide is right here. These 3 steps. 1950s, this was the early stages with the Turing test and early logical thinking. Around 1950s, they were able to get a computer to win at checkers. That was a pretty big accomplishment. Not as complicated a game as, say, chess or Go, for that matter. And it seemed like there were some interesting developments there along those lines. And expert systems began to emerge, and they're still used somewhat. But they were thought that they would be able to take over the reasoning of the corporate world and do all sorts of amazing things. They didn't really. And so in the early 90s, people kind of lost their excitement about expert systems. Although logic-based AI has still been worked on and improved, and there's been some recent developments that successes in that. But in the early 90s-ish, we started to have the rise of machine learning tools, which are very powerful and very useful. Again, people thought this might take over the world. It didn't, but some very powerful tools came out of this. In 2000, we have interactive robo-pets, which might be considered a step backwards rather than forward, but there's definitely, robots do interesting things, right? And they have kind of quirky behavior. Autonomous navigation began to be very important with NASA. Recommendation technology, the next iteration of expert systems, really begins to be very useful. And checkers game is completely solved. In 2007. In 2010, we have the recent rise of deep learning and its tremendous successes. In the Jeopardy Championship, Google DeepMind's AlphaGo World Champion, that involved, as I mentioned, that involved deep reinforcement, on-policy reinforcement learning. And logic machines were used to solve a math conjecture that humans could not check. And this was in 2017. A real advance where this logic-based approach were going beyond what humans are capable of doing. And Alibaba 2018, language processing actually beat humans in reading comprehension exam. This was really, really difficult to do. And so before I get more on exciting things, I want to warn about winter. Something we don't think about this time of year, but it's very real, especially when it comes to AI. There is a dark side to AI history. During each of these historical epochs I mentioned, there was a boom period and a bust period, and then another one and another one. And now we're in this third cycle where it's booming still, but if history repeats itself, we have to be very careful. And this slide on the right, I'm sure you can see all those little markings there and memorize them, but really what I want you to note is that this just represents the rise, the excitement of an early development in AI, the plateau, over-promises, it doesn't deliver, and we sort of have this valley of disillusionment is what this is called. And then we start keeping working, and we actually make some steady and useful progress. As I mentioned, the logic machines were promised to basically take over. They didn't do as promised, but they're still useful, and we're able to think them through and make advances. So the important thing is while it's exciting, AI is exciting, we do need to remember that AI will not replace good science or careful research, at least not yet. And I want to mention that some of the hype really is justified. I already talked about the natural language processing capability of Alibaba, the tremendous, how many have worked with their Chinese English translation tool? Has anybody used that at all or seen it? It's very impressive. It works in real time and it's very, very good. Text-to-speech synthesis is something that we have routinely even on our iPhone. If you remember the movie 2001 Space Odyssey, one of the biggest parts of the HAL 9000 computer was this speech generation chamber, right? I don't know if you remember that. And it was like a huge room. Well, we can do that on the iPhone now. We can't do the other things HAL could do, including take over, anyway. But we've really come a long ways with natural language processing. And one of the projects that I'm working on is very interesting. There's the possibility of causal textual analysis, where you look at causal effects of topics covered in text. Computer vision is something we've made tremendous advances for. And to a large extent, this is applied somewhat routinely in Facebook and other places. Object face recognition, scene and image segmentation. Here's a picture of some segmentation of cell nuclei. You can see the little purple circles here. The task here was to have humans look at these slides and try to identify what the nucleus was. The goal here is to understand, in the Purvis lab, is to understand the cell cycle to a point where we actually know when it's going to change stage, like reproduce or die or something else, although there's many more stages than that. And so what was done, this was actually an undergrad student of mine, co-advised by myself and Jeremy Purvis. We trained a deep neural net to capture these cell nucleus outlines, and it got so good it actually beat humans. Meaning that we had these humans check first, and there were some places where the AI was different, and when we probed deeper, we realized the AI was right. And so there's an example that some of these tools can do better than humans. And robotics, we don't, a lot of us in biomedicine don't think of robotics as something we worry about, but, because we think of robots when we think of robotics, but there's more to it. Self-driving cars, Teslas are able to drive pretty much by themselves, although you shouldn't. There's YouTube videos of people sleeping behind the wheel. A bad idea. You're not supposed to do that with Teslas. But there's been some successes, there's been some failures, but we're making really good progress, and probably realistically, this will be available in 5 to 10 years, a safe approach. Control systems in engineering, some of which are automated, that's an area of robotics. mHealth automated real-time interventions. So if you're doing real-time interventions in mobile health, you are actually participating in robotics research, even though it doesn't seem like it, but it is an area of robotics. Logical systems, I mentioned the theorem provers, question answering, deduction systems, satisfiability solvers. This looks at arguments to see, textual arguments to see if they're logically consistent automatically. Decision making, scheduling, airline routing, route planning, Google Maps, web search engines, medical diagnosis, precision medicine, health, machine learning is an important tool here. Game playing, IBM Deep Blue, and chess, I mentioned AlphaGo. I'm not quite as excited about game playing. I don't see at first I didn't see the relevance of this to biomedical research, which is my area. However, we can learn a lot by game playing technologies. And there's a lot of situations where these entertainment areas can bring over to science. We all know about the success of GPUs, for example, which started off in animation, right, and moved over to science. One of the very impressive successes recently is in this convolutional neural net that was developed in 2018 that's able to accurately classify 95% with 95% accuracy skin cancer diagnoses. This is of a list of about 1,000 different skin cancers. There's many, many kinds. And it tends to be a little more accurate than a human dermatologist, which is very impressive, I think. So there's exciting things. Brain-computer interface, non-speech communication, being able to walk again. There's been some promising developments of devices that can read EEGs and begin to have a person actually walk a device even though they themselves, their muscles are not responding. Next generation radiology, AI-guided administration, I'm thinking hospital administration, but it could be other things. This could also involve improving care in developing nations where maybe there could be some aspects of the care that could be automated to a certain degree. Intelligent clinical trial recruitment, this is of interest to people in medical research. And better strategy for emergency visits. We find a person comes in the emergency room, do they need to have something first before they have the medical treatment? Sometimes with certain diseases like cancer, they may need a psychiatric help before you can carry on with the other ailments that they're dealing with. Intelligent social media. So one of the things that some of us are concerned about is that some of the AI tools that Facebook uses, maybe some of you know this, is actually driving people to behavior that's not healthy. So usually they've discovered that the Facebook AI selects things that will increase conspiracy theories and also controversy. Okay, these are things that people like and it draws them to Facebook. And the AI is just saying, hey, this works, so let's do it. It's not deliberate. Nobody's trying to be mean or ruin society. It's just that it's seeking after this utility, which is clicks, number of clicks. And it found something that really works. So the question that we have is, can we use social media to do good things instead of bad things? And so one of the goals that some of us are seriously working on is develop strategies to reduce vaccine resistance. Right now, there's an anti-vax movement. As you may know, the number of measles cases right now is the same as it was before the vaccine that got rid of it. So it's really frustrating. And this could be used for identifying, mitigating false health content generally, because also another issue that's happening in social media is the rise of falseness. Truth is not as important as it used to be. I'm being facetious, but that's what happens, unfortunately, in the social media world. And early warnings of emerging health threats. There have been some false starts in this area, but it's also promising. So going back to the dark side of AI, we need to be very cautious about these things. And there's several things that worry me, and I want to just talk about those a little bit. One is the democratization of AI. What I mean by this is the software to do deep learning is easily available. You can get stuff download it, you can take online classes, you can basically be armed with a nuclear weapon and go use it, almost. The pros are that that does increase awareness of AI and greater citizen awareness, and hopefully we can do citizen science research, but the cons are serious. This is that there's an insufficient understanding of the statistical concepts that are needed whenever you learn from data, and the caution that you should take, and the reproducibility principles, and they're going to have too many false positives. And you can do this without AI, but it's going to especially happen with AI. A project I worked on a couple of years ago, we're looking at how do we look at when emergency room visits are out of sync with normal, say there's too many asthma, and we want to have an alarm, so if there's anthrax out there, we'll find it, right? That sounds like a really good thing. Well, if you use standard basic approaches like Q-sum methods, it works pretty well. The only issue is that for every true positive, there are thousands of false positives. Very expensive. And so there it's important to use spatial modeling and other techniques to tighten up those estimates. And you can get it down to maybe 3 to 1 false positives, or even 100 to 1, which is way better than thousands to 1. Well, if you have billions of people working on AI discoveries, not knowing what they're doing, claiming all sorts of things, it can be really interesting, confusing time. So we want to be very careful about that. One of the real bad side effects is it could make AI seem like it's not useful because it's being used so poorly, right? And so it can destroy. Poor use of technology can lead to people misunderstanding and distrusting the technology. It's not because the technology is bad, because it's been used poorly and unwisely. And the risk of bad actors. Evil people could use AI for harm. It's already happening. Automated AI tools could have unintended adverse consequences. So this is the unintended side effect. Sometimes when you do these, use these machine learning, like Facebook's machine learning tool, you get this unfortunate consequences that start hurting society. But other possibilities, to do precision medicine, you might get let's say we're applying precision, maybe not to medicine, but precision decision making generally. We want to use it for allocating funds. Okay, and our AI, or machine learning tool, gives us a strategy. It looks all great, but unfortunately, unbeknownst to us, it disproportionately harms underrepresented minorities, let's just say. So that's something we would want to watch for in our AI. We want to look for and control the unintended consequences. Machine learning is powerful, but it will blindly go after the utility function that's been assigned. We need to be very careful about that.
Hey, what's that middle image?
I'll tell you about that in just a moment. Just give me a second. And I'll come right back to it. That's my next. So my point is that good research takes care. It doesn't necessarily take time, although it often does, but it takes care. Easy implementation leads to impatience in research and can cause us to overlook important things. This leads to inadequate evaluation and peer review, and promising advances may be dismissed early due to poor implementation. And so it doesn't just hurt the fact that we get this nuisance outcome and results, it can actually affect the credibility of the field, which is a problem too. And study design is crucial. Now, you asked about this part here. This is an original score from Beethoven's Fifth Symphony. And that is widely regarded as the greatest symphony of all time, easily. And Beethoven was I have interest in this stuff, and you can dispute this if you know more about Beethoven than me, it's fine. But I'll tell you basically a nutshell story idea. Beethoven was very, very good at improvising. He could sit down at the piano and play something. In fact, he was playing something, Mozart walked by and said, "That's pretty good, that's pretty good." And Mozart, of course, had pretty high standards, right? Anyway, turns out that they said, "Oh, he just sat down and made that up." Mozart said, "Whoa, this guy's really good." He was really shocked at how impressed, how good he was. So Mozart didn't need a lot of time to write really good music. However, the Fifth Symphony wanted to do something very, very different. And he spent 4 years crafting it very carefully. And I could give you all sorts of reasons what are amazing about it, but intellectually it is profound. It's a total new way of thinking about music. And it's a powerful piece too. It's a little bit overplayed, so don't kind of get the fun out of it that we did when we were young and heard it for the first time. But I put this here because I feel that we want to do good work in this area, and that it takes care. So it's just more symbolic stuff. It's not anything really AI related. Okay, so something completely different now. I just wanted to touch on that because I think as statisticians, we often dismiss AI as for the people doing computer science and stuff, but anything involving data, especially biomedical data, statisticians have a role to play. And we need to be open and able and willing to increase our education in computational issues and AI issues, collaborate on teams. A lot of the work that I've been doing with AI involves teams of people with different expertise. I bring something to the table, other people bring something to the table, and we're able to solve fairly difficult problems. And I just want to point that out there that I think AI is part of the statistical domain as well, at least it needs to be. Okay, so now going back to my first slide. So this is a project that we've been working on for a couple of years now, and the idea is to come up with minute-by-minute help for patients with type 1 diabetes, decision support. So this includes, and what we have here, as I mentioned before, the red dots are insulin boluses. The black line is glucose level. Glucose should be between about here and about here. So this person is kind of high, honestly. And then they exercise, and that pulls the glucose right out of their system quickly. And actually, they're dangerously low. And what can happen if you're down this far for too long, it can kill a person with type 1 diabetes. It's very dangerous. The high can be very dangerous, but the effects are somewhat slower in accruing. But this person then ate a bolus of food, which gave them a rush of glucose into their blood and pulled them out, although it went a little high here, so I had to take insulin. You can see how hard it is for this poor patient to keep their blood glucose level in a safe range. So there are what are called artificial pancreases that are closed-loop control theory-based approaches that monitor glucose and try to act like a pancreas. The difficulty with them is they don't adapt very well to changing metabolism. And they're also they're not very available. So very few patients have access to them. So our goal here is to create an app that can help a patient stabilize their blood glucose, but importantly, help them to be able to exercise safely. So we actually have AI on 2 scales. One scale is immediate 50-minute by 50-minute assessment of what they need to do perhaps to control blood glucose. But then, if they want to exercise, we learn from a series of their exercise experiences and help the patients prepare for exercise by eating, doing proper things before exercise for a couple hours, during exercise, and then after as they cool down from the exercise. Metabolically, it takes at least 4 hours, sometimes more, depending on the kind of exercise. So that's the goal of this. And we use a market decision process framework, which is one way to think about control theory. Most of the time people think of differential equations for control theory, but there are all sorts of different ways. Market decision process is one. And so what we have here is we have a patient's data at a series of time points. This is their state. In our case, it's a Euclidean vector. So this is not traditional Markov process where we have finite states, number of states. These are entire Euclidean spaces, so they're uncountable number of states. And then we have an action that would take, and then a new state. And the utility is a summary of both. This basically, it can be a function of the change. It can also be a function of the action itself. It may cost, for example. The utility is some assessment. And our goal is to come up with action strategies, policies, that maximize or minimize whatever utility function we're looking at, usually by what's called a discounting average, where one looks at either proximal effects or distal effects. And the closer gamma is to 1, the more distal the effects are. And if gamma is 0, it means we're only looking at immediate changes. But V-learning is an interesting approach that is an alternative to Q learning for market decision processes and other reinforcement learning tools that uses this idea of focusing on the policy that I mentioned earlier. It's a form of outcome-weighted learning. And it tends to work really, really well in this environment. And we're able to reduce, according to our data estimates, blood glucose rates by about half compared to other competing reinforcement learning tools or management we've looked at. This is a paper that's in press in JASA, and we applied it to some health data that's actually the data I presented earlier. The state includes insulin use, food intake, physical activity, blood glucose, other demographic and dietary factors. Actions include take insulin, a certain amount, eat, exercise, combinations for exercise, and then various combinations of those strategies. Exercise actually is one good way to bring your blood glucose down, but you got to be careful with it. So you don't always need to take insulin to do it. You can exercise something that's better. And so as I mentioned, we were able to reduce for a particular patient their time out of range by 64%, which is very significant. This is just a picture. So we've been working on an app that we have finished. Eric Labor's not here today, I don't see him. Eric and I and one other, Beth Mayer Davis in nutrition, and several other individuals are collaborating on making an app. We finished the, this is just some of the user interface. Has the planning mode and the standard mode. Standard is when not exercising, planning is when preparing to exercise. This is the user interface. It's called Hydra, and we're going to be doing focus groups at the end of this month, early June, to sort of finalize the design, and then we're trying to identify, and we have a couple potential startup companies that will help us take this to the next phase of production and testing in humans. Looking to the future, I think I'm still okay with time, right? Am I supposed to wrap it up soon, David?
I think we have an hour. But yes, this is, you know,
Okay, I'm gonna start
ready
wrapping
for
up.
landing and take some questions. That'd be
I have a whole hour? Wow, okay, I didn't know. So looking to the future, what are some of my thoughts about these things? And I really like this quote. It's been attributed to many people, but we think it goes all the way back to Abraham Lincoln. The best way to predict the future is to create it. Which which I didn't know is something. I've heard it in recent decades by various people in company. John Wimler likes to say it, but it's probably Abraham Lincoln as far back as we know. So here's my thinking. We need to be able to do good AI and machine learning. The statistical foundation is essential for various reasons like we've articulated, but the computing foundation is essential. Computing expertise. There's many insights we can gain. Efficiency of algorithmic computation, but also other aspects about data and working with data and images and other things. A domain expertise is essential. Rigorous team science with depth. So we're thinking about training the next generation. With increased democratization, I think it's very important to teach the fundamentals of statistical concepts to everybody, whether they're going to be an English major or not, so they understand the context of AI and what it means to society, how to think about it through, and how to evaluate. Because many of the concepts I talked about earlier for precision medicine, they're just concepts, they're not math. I mean, there is math, but we need to get people who are not mathematical to engage in these ideas too. And also, I think all domain areas need some knowledge of AI and data science. And also, I think we need to do a little more team science type training. I know that that's happening at many universities, but I think it's increasingly important. Another thing that I think is surprisingly neglected is the communication about AI and machine learning. One of the interesting privileges I had was when I went to Beijing in November, I visited Didi Chuxing. Does anyone know who that company is? It's kind of their Uber, but it's bigger than Uber. They have a huge data science team with amazingly talented people. And I was invited to speak there and get to meet them, but they also brought me to a room where they had these displays, the 3D-dimensional interactive data science-based displays. I was just blown away. The power of being able to communicate with using AI and data science, there's new ways of thinking, and we can actually change the way our brains respond to information. And so I think that we need to think about this as a legitimate area of research and be able to emphasize and work on it a little bit more, as well as learn to communicate about these concepts. And the role of public opinion is crucial. If they view these as good methods that are in good hands, we'll be able to have support. And we need to watch those things. And also, there's other aspects of ethics. Ethics of AI is highly non-trivial. We need to preserve privacy on the one hand, but we need to break down barriers for data access on the other, and those are actually in direct conflict. Or at least it seems right now. There's some interesting developments which seems to make that possibility to not be as controversial. We need to study unintended consequences of what we do, and we need to develop strategies to anticipate and reduce threats from bad actors. We need to pay a lot more attention to that, I think. So, concluding, there are many useful new methods in AI and machine learning for precision medicine discovery and other areas. We're probably entering a golden age. I say probably because I don't want us to go in the tanking. I don't want to have the tanking part of the AI winter. But I think that we're still learning. We're still entering a golden age of this area. Statistical inference principles are key. We have a lot of work to do. There's lots of room for creativity and problem solving. And we need to really embrace transdisciplinarity. And obviously, computational scientists need to become more statistical, and statisticians need to become more computational. So that's where I will leave it.
Yeah, so I guess this is referring to as the off-policy learning, what you're doing with your diabetes app.
Yeah.
And I'm just wondering, how do you do that? Because your algorithm can't just wait around for your diabetic patient to, undergo their next bout of activity.
Yeah.
So, and you can't, how do you create the reward function, right?
It's a very, very good question. So,
really solve the
yeah. So for one thing, we actually do get the reward function is not so difficult. It's time within range. Some sort of scaled time within range is not such a difficult thing to come up with. But the challenge is, one of the things we can take advantage of is that most people are not robotic in the way they treat their own insulin, their own type of diabetes. And so there ends up being a little bit of natural explanation that goes on. And so the propensity score underlying these various transitions is pretty balanced away from 0 and 1. That's one thing we can take advantage of. The second thing is, I think, that is something, as you get closer to getting the right answer, you have the problem of, if you do it too greedily, you'll stop exploration. What if the person's metabolism changes? You'll never know. So one of the things that we're working on and thinking about is, what is the best balance between exploration and exploitation when you're doing this kind of learning? And that's still an unsolved problem, but we know crudely that there's, something like 20% exploitation, 80% exploration initially. Maybe that changes, but you keep away from any one of them going to 0 or 1. That helps a lot. But the other thing you can do is you can actually proactively design your system so that it does this. And so something called Thompson sampling is kind of helpful here. And Thompson sampling goes from the 1930s, but the idea is that you change your randomization so you build information of some kind. Traditionally, it's been viewed as a greedy approach where everybody gets the highest chance of getting the best treatment in the trial. But you can actually tweak it in a lot of different ways where you can maximize information for people just after the trial's completed. Or you can trade off between these two in such a way that you have nearly maximum adaptation, but you have the ability to always have this little edge of exploration that keeps you, aware. And so, while that's not a perfect solution, it helps us, I think, make progress in the area. So, another example that we're working on is in a project we're working on in Zambia based on Gates Foundation funding. We are going to be looking at the delivery of mothers delivering babies and trying to reduce the complications associated with birth. They're very severe there. And what we want to do there is observe what's going on in the room without interfering a lot, so that there's sort of a natural experiment. Some countries have such a regimented approach to the way to do medical care that if you look at the propensity score, it's just flat line. There's just one thing they do and they do it the same way. And so you can't get any information. So what we want to do is design the studies so they're is a reasonable, ethical place where we have a nice, natural experiment going on. And when we think about this for EPIC data, for example, of hospitals, which we're also thinking about, there, we think clinicians, because we're working with a lot of clinicians, are very open to the idea as we come up with something called continual assessment, where you're always learning. We learn from the existing data, but we have some randomization always that's around a healthy, nothing crazy, we're not going to randomize them the wrong thing, but clinicians are very open to this because a lot of the time they don't really know what's the best. So I'm not saying those are all butterflies and unicorns, but I think that there is a smart way to do this that can keep us from being too greedy too quickly.
Okay.
That helpful?
Yeah.
David?
This is slightly related. At several steps in your talk, the assumption was that you had a definite utility function that was known. And my sense is that people have many different utility functions and don't know what they are.
Yes.
Is there any way to make progress on that front?
Yeah, so I'm glad you asked that question. I don't have it right here, but one of the things we actually have been doing, and we have a paper came out on biometrics, actually 2018, where we use item response theory to gauge patients' priorities between preferences. Now the challenge with that is calibrating that utility function, because you may get an idea of their latent score on the balance between these two, but you don't necessarily know how that translates to precise weighting between outcomes. So there, we also have working on that paper, and we think we have a solution for it. Another thing that you can do is, I mentioned a little bit before about learning from physicians. So we have an interesting application where we had nice natural history of patients treating people with bipolar disorder. And we really hope the physicians are doing the best they can. And we actually can measure the outcomes and model it as a function of patient features. And one of the things that we can do is a variant of reinforcement learning is we assume that clinicians kind of know how to balance the two outcomes. In this case, it was mania and depression, because treating depression can induce mania. So they're conflicting outcomes. You want to control both. That they had a good sense of how to balance this, but they didn't know how to do it with error. So what we did is we made an assumption that physicians get it right with non-zero probability. And we modeled that probability as logistic regression as a function of patient features. Then we also separately modeled the weight that they were targeting as a logistic regression. And then we did models, rich regression models of the two outcomes, so that we could actually look at what happened in the data. And this allows us to actually, we really believe that physicians get it right with non-zero probability. You can actually estimate all of those parameters. It turns out that it's a very funky limiting distribution on the boundary between the two groups. All of the asymptotics lies on the boundary. So it's very interesting asymptotics. But you have enough power that we were able to get a significant difference. We were able to figure out what physicians were doing that was working, and then be able to apply it and estimate how big of an improvement it would do if they actually use this rule that they're sort of trying to use, but they're not fully aware of it. I know that sounds really weird, but that's something you can do if you believe that they are at least right with non-zero probability. If they're not, then you can't really leverage their decision making. And this is something that Erica Moody has mentioned in some of her work earlier on, that sometimes we should take advantage of the fact that clinicians are right some of the time. When we look at observational data, it's not just nuisance that they are assigning the treatment the way they are. Sometimes it might be, they learn in med school and they're not thinking, but that's not what the case a lot of the time. They're really thinking about it, and there's a lot of information there. So anyway, it's a long answer to this.
Thank you.
Yes?
So when you're working on the actions that you're taking for these diabetes patients, is there any type of thing that you're using to control, say, how often they'll eat, or that they don't exercise while they're eating because that would be unpleasant? Like, is there any type of consideration for that?
Yeah, those are very good points. What you call it a sort of practical tweaking of the thing. Yes, we absolutely have those. And they're sort of, you do a mixture of ad hoc approaches where you just take your output and then make sure it doesn't say anything ridiculous, to trying to be more proactive with it. But we do have to take that into account for sure. That's a good point. All of your recommendations have to be reasonable recommendations, so, and safe. And there will be the need for FDA to review this. We were trying to do it without having insulin recommendations, because that puts it squarely in the need for FDA approval. But we realized that a lot of the successful policies that was coming up with involved strategizing the insulin intake. We realized, hey, it's important, so we're going to just bite the bullet and make sure that this passes FDA muster, which is probably a good idea anyway. It just takes more time. Good question.